725.52 allows open-air splices and does not require them to be in a junction box. Chapter 3 requirements can also be enforced, but they cannot be used to override the specific requirements of 725.52. 725.52 states, splices shall be made only in junction boxes, fittings, or other enclosures approved for the purpose. Chapter 3, Section 300.15 states, conductors shall be installed in raceways, unless otherwise permitted by this code. The two sections are not in conflict because 725.52 specifically allows open-air splices in Class 2 and Class 3 circuits. Class 2 and Class 3 circuits are low-voltage power circuits that have specific limitations on voltage and current, which are designed to reduce the risk of electrical shock and fire hazards. Because of these limitations, the National Electrical Code, or NEC, provides some exceptions to the general wiring methods required for higher voltage circuits. One such exception relates to splicing. Splicing is the joining of two or more conductors to create a continuous electrical path. Generally, the NEC requires that splices be made in SI-approved enclosures such as junction boxes. This requirement is in place to provide mechanical protection to the splice, preventing it from being damaged and creating a potential electrical hazard. Junction boxes also contain any sparks or arcs that might occur at the splice point, reducing the risk of fire. However, for Class 2 and Class 3 circuits, 725.52 of the NEC provides an exception to this general rule. It allows splices to be made without an enclosure, essentially open-air splices, under certain conditions. This allowance is based on the lower risk associated with these low-voltage, limited-energy circuits. Now, to understand the interaction between 725.52 and Chapter 3 of the NEC, it is important to know what Chapter 3 covers. Chapter 3 of the NEC deals with general wiring methods and materials. It outlines the requirements for installing conductors, raceways, cables, and other wiring components. Section 300.15, which is often referenced in conjunction with 725.52, falls under Chapter 3 and addresses the requirement for using junction boxes or enclosures for splices. This section states that conductors must be installed in raceways unless otherwise permitted by the code. The phrase "unless otherwise permitted by this code" is crucial. It acknowledges that there are exceptions to the general rule, and 725.52 is one such exception for Class 2 and Class 3 circuits. So, how do these two sections interact? The key is that 725.52 provides a specific allowance for open-air splices in Class 2 and Class 3 circuits. This allowance takes precedence over the general requirement in 300.15 that all splices be enclosed. However, it is important to note that 725.52 does not completely negate the requirements of Chapter 3. Other applicable requirements in Chapter 3, such as those relating to conductor ampacity, insulation type, and support, still apply to Class 2 and Class 3 circuits. The exception in 725.52 only applies to the requirement for enclosing splices. To clarify further, consider a scenario where you are installing a Class 2 circuit to power a landscape lighting system. According to 725.52, you are permitted to make splices in the conductors without placing them inside a junction box, provided that the splices are made in a manner that ensures good electrical contact and mechanical strength, such as using approved connectors. However, you must still ensure that the conductors are of the appropriate size for the load they will carry, that they are suitable for the environmental conditions, such as direct burial if they are underground, and that they are properly supported. These requirements are all found in Chapter 3 of the NEC. Now, it's important to also consider listing and labeling. While 725.52 permits open-air splices, it also includes the caveat that splices must be made using methods and materials approved for the purpose. This means that the connectors or splicing methods used must be listed and labeled for use in Class 2 and Class 3 circuits, and they must be installed according to the manufacturer's instructions. This requirement ensures that the splices are reliable and safe, even though they are not enclosed in a junction box. In summary, The NEC allows open-air splices in Class 2 and Class 3 circuits under certain conditions, as specified in 725.52. This allowance is an exception to the general rule in 300.15 requiring all splices to be enclosed. However, other applicable requirements in Chapter 3 still apply, and all splices must be made using listed and labeled methods and materials. Always consult the latest edition of the NEC and follow the manufacturer's instructions for all electrical work. To further elaborate on the nuances of 725.52 and its interaction with Chapter 3, let's consider some specific examples and potential scenarios. Firstly, consider the type of connectors used for open-air splices. While 725.52 allows these splices, it's crucial to understand that not all connectors are created equal. The NEC mandates that any splicing method or connector used must be listed and labeled for the specific application. This means that the connector has been tested and approved by a recognized testing laboratory such as Underwriters Laboratories or all, to ensure it meets certain safety and performance standards. For Class 2 and Class 3 circuits, the connectors should be specifically rated for low voltage applications and suitable for the environmental conditions in which they will be used. For example, if the splice is exposed to moisture, a waterproof connector should be used. Common types of connectors used for open-air splices in Class 2 and Class 3 circuits include crimp connectors, insulation displacement connectors, and wire nuts specifically listed for low voltage use. It's important to follow the manufacturer's instructions when installing these connectors to ensure a proper and reliable connection. Secondly, let's discuss the routing and support of the conductor. While 725.52 allows open-air splices, it does not exempt the conductors from the general requirements for support and protection. Chapter 3 of the NEC provides detailed guidelines for how conductors should be routed and supported to prevent damage and ensure safety. For example, conductors should be supported at appropriate intervals to prevent them from sagging or coming into contact with other objects. They should also be protected from physical damage such as abrasion or impact. In some cases, it may be necessary to run the conductors inside a conduit or other protective raceway, even if the splices are made in the open air. The decision to use a raceway will depend on the specific application and the level of risk involved. Thirdly, consider the ampacity of the conductors. Ampacity refers to the current carrying capacity of a conductor. Chapter 3 of the NEC includes tables that specify the ampacity of different types of conductors based on their size, insulation type, and temperature rating. When installing Class 2 and Class 3 circuits, it's essential to ensure that the conductors are of the appropriate size for the load they will carry. This means calculating the total current that the circuit will be expected to carry and selecting conductors with an ampacity rating that is equal to or greater than that value. It's also important to consider any directing factors that may apply, such as those for ambient temperature or the number of conductors in a raceway. Failure to select conductors with adequate ampacity can result in overheating, insulation damage, and potentially a fire hazard. Fourthly, let's talk about the location of the splices. While 725.52 allows open-air splices, it's still important to consider where those splices are located. Splices should be located in areas where they are accessible for inspection and maintenance. They should also be protected from physical damage and environmental factors. In some cases, it may be necessary to locate the splices in a more protected location, even if a junction box is not required. For example, a splice might be located under an eave or inside a weatherproof enclosure to protect it from rain and snow. Fifthly, consider the voltage drop in the circuit. Voltage drop refers to the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or perform poorly. Chapter 3 of the NEC includes recommendations for minimizing voltage drop in the electrical circuits. When installing Class 2 and Class 3 circuits, it's important to calculate the voltage drop to ensure that it is within acceptable limits. This can be done using Ohm's law and the conductor's resistance per unit length. If the voltage drop is too high, it may be necessary to increase the size of the conductors or reduce the length of the circuit. Now, let's address some common misconceptions about 725.52 in Chapter 3. One common misconception is that 725.52 completely eliminates the need for junction boxes in Class 2 and Class 3 circuits. While it does allow open-air splices under certain conditions, it does not prohibit the use of junction boxes altogether. In some cases, it may be preferable to use a junction box, even if it is not required by the NEC. For example, a junction box may provide additional protection for the splices or make it easier to access them for maintenance. Another misconception is that any type of connector can be used for open-air splices in Class 2 and Class 3 circuits. As mentioned earlier, the NEC requires that the connectors be listed and labeled for the specific application. Using unapproved connectors can result in unreliable connections and potential safety hazards. Another common misconception is that Chapter 3 requirements do not apply to Class 2 and Class 3 circuits. While 725.52 provides an exception to the general rule requiring enclosed splices, it does not exempt Class 2 and Class 3 circuits from all of the requirements in Chapter 3. Many of the requirements in Chapter 3, such as those relating to conductor ampacity, insulation type, and support, still apply to Class 2 and Class 3 circuits. To provide a more concrete understanding, let's consider some practical examples. Example 1: Landscape lighting circuit. Imagine you are installing a Class 2 landscape lighting system. The system consists of a low-voltage transformer that steps down the voltage from 120 volts to 12 volts, and several LED landscape lights that are connected to the transformer using low-voltage cables. According to 725.52, you are permitted to make splices in the low-voltage cables without placing them inside a junction box. However, you must use connectors that are listed and labeled for use in Class 2 circuits and suitable for outdoor use. You must also ensure that the cables are properly supported and protected from physical damage. Furthermore, you must select cables with an ampacity rating that is sufficient for the total load of the landscape lights. Example 2: A thermostat control circuit. Consider a thermostat control circuit in a heating and cooling system. The thermostat is connected to the furnace or air conditioner using low-voltage wires. These wires carry signals that control the operation of the equipment. According to 725.52, you are permitted to make splices in the thermostat wires without placing them inside a junction box. However, you must use connectors that are listed and labeled for use in Class 2 circuits. You must also ensure that the wires are properly supported and protected from physical damage. Furthermore, you must select wires with an ampacity rating that is sufficient for the current that the circuit will carry. Now let's discuss some additional considerations when working with Class 2 and Class 3 circuits. Firstly, it's important to understand the difference between Class 2 and Class 3 circuits. Class 2 circuits are defined as circuits with a voltage of not more than 30 volts alternating current or 60 volts direct current, and a power limitation of 100 volt amps. Class 3 circuits are defined as circuits with a voltage of not more than 30 volts alternating current or 60 volts direct current, and a power limitation of 0.5 volt amps. The main difference between Class 2 and Class 3 circuits is the power limitation. Class 3 circuits have a lower power limitation than Class 2 circuits, which makes them even safer. Secondly, it's important to be aware of the potential hazards associated with Class 2 and Class 3 circuits. While these circuits are considered low voltage and limited energy, they can still pose a shock hazard under certain conditions. For example, if the insulation on a conductor is damaged, it may be possible to receive a shock if you come into contact with the conductor. It's also important to avoid creating short circuits, which can cause excessive current flow and potentially damage the equipment. Thirdly, it's important to follow safe work practices when working with Class 2 and Class 3 circuits. This includes energizing the circuit before making any connections or repairs, using insulated tools, and wearing appropriate personal protective equipment, such as safety glasses and gloves. It's also important to inspect the wiring and equipment regularly for any signs of damage or deterioration. To recap, 725.52 of the NEC allows open-air splices in Class 2 and Class 3 circuits under certain conditions. This allowance is an exception to the general rule in 300.15 requiring all splices to be enclosed. However, other applicable requirements in Chapter 3 still apply, and all splices must be made using listed and labeled methods and materials. When working with Class 2 and Class 3 circuits, it's important to understand the difference between these two types of circuits, be aware of the potential hazards, and follow safe work practices. Always consult the latest edition of the NEC and follow the manufacturer's instructions for all electrical work. The NEC is updated regularly, typically every 3 years, so it is essential to refer to the most current edition for the latest requirements. State and local jurisdictions may also have their own amendments or interpretations of the NEC which must be followed. Moreover, electrical codes and standards are complex and can be difficult to interpret. It is always advisable to consult with a qualified electrical inspector or engineer if you have any questions or concerns about the proper installation of Class 2 and Class 3 circuits. Furthermore, continuing education and training are crucial for electrical professionals to stay up to date on the latest codes, standards, and technologies. Many organizations offer courses and certifications that can help electricians and other electrical workers enhance their knowledge and skills. Now let's delve into some specific scenarios where the application of 725.52 in Chapter 3 might be particularly relevant. Scenario 1: Low voltage lighting systems in swimming pools. Low voltage lighting systems are often used in and around swimming pools to provide illumination and create a pleasant ambience. These systems typically use Class 2 or Class 3 circuits to reduce the risk of electrical shock. When installing these systems, it's important to follow all applicable requirements in the NEC, including those relating to grounding, bonding, and wiring methods. According to 725.52, open-air splices are permitted in the low-voltage cables, provided that the splices are made using listed and labeled connectors that are suitable for wet locations. However, it's also important to consider the location of the splices. They should be located in areas where they are accessible for inspection and maintenance, and they should be protected from physical damage and exposure to chemicals. In some cases, it may be necessary to locate the splices inside a weatherproof enclosure to provide additional protection. Scenario 2: Security systems and alarm systems. Security systems and alarm systems often use Class 2 or Class 3 circuits to connect sensors, detectors, and other devices to the control panel. When installing these systems, it's important to follow all applicable requirements in the NEC, including those relating to wiring methods, overcurrent protection, and grounding. According to 725.52, open-air splices are permitted in the low-voltage wiring, provided that the splices are made using listed and labeled connectors. However, it's also important to consider the security aspects of the installation. The wiring should be installed in a manner that minimizes the risk of tampering or damage. In some cases, it may be necessary to run the wiring inside a conduit or other protective raceway to prevent it from being accessed by unauthorized individuals. Scenario 3: HVAC control systems. Heating, ventilation, and air conditioning, or HVAC, systems often use Class 2 or Class 3 circuits to control the operation of the equipment. These circuits may be used to connect thermostats, sensors, and other control devices to the furnace, air conditioner, or other HVAC equipment. When installing these systems, it's important to follow all applicable requirements in the NEC, including those relating to wiring methods, overcurrent protection, and grounding. According to 725.52, open-air splices are permitted in a low-voltage wiring, provided that the splices are made using listed and labeled connectors. However, it's also important to consider the environmental conditions in which the wiring will be installed. If the wiring is exposed to extreme temperatures, humidity, or other harsh conditions, it may be necessary to use conductors and connectors that are specifically rated for those conditions. Another important aspect to consider is the proper identification and labeling of Class 2 and Class 3 circuits. The NEC requires that all electrical circuits be properly identified to prevent confusion and ensure safety. This is especially important for low-voltage circuits, which may be easily mistaken for other types of circuits. Class 2 and Class 3 circuits should be clearly labeled to indicate their voltage, current limitation, and classification. This can be done using tags, labels, or other markings that are permanently attached to the wiring or equipment. The labeling should be legible and durable, and it should be placed in a location where it is easily visible. In addition to labeling the circuits, it's also important to maintain accurate documentation of the electrical system. This documentation should include wiring diagrams, circuit schedules, and other information that is necessary to understand the system. The documentation should be kept in a safe and accessible location, and it should be updated whenever any changes are made to the system. Accurate documentation can be invaluable for troubleshooting problems, performing maintenance, and ensuring the safety of the electrical system. In conclusion, understanding the interplay between 725.52 and Chapter 3 of the NEC is crucial for safely and effectively installing Class 2 and Class 3 circuits. While 725.52 provides an exception to the general rule requiring enclosed splices, it does not exempt these circuits from all of the requirements in Chapter 3. It's essential to use listed and labeled connectors, follow safe work practices, and consult the latest edition of the NEC to ensure that all installations are in compliance with the code. Remember, electrical safety is paramount, and it's always better to err on the side of caution. If you have any doubts or questions about the proper installation of Class 2 and Class 3 circuits, consult with a qualified electrical professional.